We now start talking about simple storage elements such as latches and flip-flops and how they're constructed and how different or similar they are. We'll start by talking about SR Latch, which stands for Set or Reset Latch. This particular diagram shows me that we can construct an SR Latch using a couple of cross-coupled NOR gate. And we call it cross-coupled NOR gate is because the output of one is connected to the input of the other, and the output of this one is connected to the input of this one, and this cross-coupling creates what we call a storage element. So why do we say that it creates a storage element? Because as it turns out that this circuit here does not only depend on the input, meaning the output in here Q does not only depend on what input there is, but it depends on the other output. So this output in here Q depends on Q prime and so forth. So that's how we create a storage element. So an SR latch is probably one of the simplest storage elements there is. So let's see how it actually works. And we're going to explore it by just exploring its characteristic table. And we call this a characteristic table because it's not a truth table, because now we're not dealing with combinational circuits anymore. And I'll emphasize this in a second. So let's get started. So this one here tells me, again, set stands for S stands for set, which means that Q should be 1, and R stands for reset, which means Q should be 0. So let's see what is it actually doing. So I'm going to actually put S here is 1 and the reset here is 0. Okay. So what this tells me is the following. Well, I am dealing with NOR gates. So just as a quick reminder, in a NOR gate, the output is always 0 except when both inputs are 0. So the minute you see a 1 at its input, that means the output will be 0. So I'm just going to write it here so that we don't confuse it. So if you see in the input, you see a 1, that means the output is for sure a 0. Okay, that's for sure. Unless you see a couple of zeros, the output is always zeros. Okay, so that's fine. So that tells me that the output here is 0, and I can propagate it back to the other input in here. And now I do see these couple of zeros in here, so that means the output here should be 1. And I can say on the characteristic table that this actually set Q, and that's exactly what I expected. Set is 1, reset is 0, and so forth. So now we change a little bit, and now the inputs now goes to 0, 0. So the input goes to 0, 0. So what I'm going to say is, okay, that's fine. We're going to do this here. And of course, this 1 got propagated here, so I'm just going to make sure that we have it. But the set now is at 0. And again, I will take a look at this one here. This is a 0, so I'll have to take a look at the other input. The other input is 1, and according to that one here, I should have an output of 0. So that's fine. So this 0 here and this 0 here will give me an output of 1. So this is a no change condition. So I'll have to have 1 and 0, and this is here we say no change. Okay, no change. All right. So now we move on to the next step in here, which I expect, since R is 1, I expect it to reset Q to 0. So let's see if that will actually happen. So we're going to do this here. I'm going to do 1, and now the input is 1. That means the output is definitely 0. So I'll have to change this guy in here. Okay. And of course, if you put this as 0, this should be at 0. And now the output in here is, or the input here is 0, 0. That means the output here should change to a 1. And now we have this as a 1. So now this did reset those to this case. Okay, so Q is 0. And just as a note and a reminder, Q prime is equivalent to Q bar. So you can actually say Q or Q bar. And it's just opposite or the not of Q. And that's what we're seeing in here. Okay, so we move on to the next stage, and as we might expect, it's a no change condition. It's like a 0, 0. So let's see if that will actually happen. So we're going to do this as a 0. I believe I forgot to propagate this guy in here to 1. Okay, so I'll have to just correct this little guy in here. So now this is a 1. So now I put a 0, 0. Well, I know that there's this input here is at 1, and according to this rule here, I have to have an output of 0. So that stays. And of course, this 0 propagates in here, and I have a 0 in here, so the output is 1. So this is here is stay. So what I have is I have a 0 and I have a 1, and that's also a no change. Okay, so that's good. So now last, we have an unwanted condition. Usually we call it the illegal condition. Let me explain why we call it that way. So we're going to change S and R simultaneously at the same time to be 1. And according to this rule in here, if I have a 1 at the input, the output will be 0. So both of the output will be 0 at that point. Okay, so we're going to have 0 in here, and we have to have a 0 in here. Of course, I have to propagate this here to be a 0, and I have to propagate this here to be a 0. So that's fine. So technically, this will give me a 0, 0. So first, it's actually opposite to what I assume. I assume Q and Q bar should be opposite of each other. So this is why we call it an illegal condition. But more importantly, it actually leads to a very unwanted situation. So let me show you. Let's assume that right after you did this, you decided that this should be a 0, 0. Let me just write this here, 0 and 0. Okay, if you decided that this should be 0 and this should be 0, let me just do that. Okay, so we decided that this should be 0 and this should be 0, and you decided to do this simultaneously. Well, the output, according to this here, this is 0, 0, so the output here should be 1, and these are 0, 0, and the output should be here 1, 1. So I am supposed to get a 1 in here, I'm supposed to get a 1 in here. Okay, which is also another illegal condition. Theoretically speaking, if I go between 1, 1 and 0, 0, 1, 1 and 0, 0, I'll oscillate between this 0, 0 and 1, 1 here input. However, as it turns out that these gates are constructed with electronic devices, and these devices are not necessarily equivalent. So there's a little bit of tolerances. And what happens is maybe the output of this one here will output a 0 before the other one changes between 1 and 0. And I might get a situation that is 0, 1 or 1, 0, and it's unknown which one it is. So it'll go through an a metastable condition, or we don't call it metastable, but it's an oscillating condition, okay, and we don't want it. So this particular situation where it's 1, 1, we usually don't care about it, and we should not use it. Okay, so where does that leave us? Well, it leaves us with this particular characteristic table in here. So we should only use it between here and here. All right, so again, I just want to emphasize why we call it a characteristic table, not a truth table, and the reason why is these ones in here. So what you see is the following. The input here is 0 and the input here is 0, but the output is 1 and 0, so Q is 1. The same input, 0, 0, does not yield the same output. It will yield output 0 for Q and output 1 for the other one. And that's why we don't call it a truth table, because it depends on the current state. And that's simply how an SR latch works. So of course, an SR latch can be composed or constructed using NAND gates. And frankly speaking, you can follow the same type of logic that we followed before, but I can tell you just in short, the only difference between the two is actually the meaning of zeros and ones. So this one here, it's flipping the 0 whenever one of the inputs is 0, that's actually the input that I care about. So in here, it tells me that probably is the reset. So since it's a reset, I'm going to say this is 0 and this is 1. Okay, let me just do this that way. Okay, and then 1, 1 is actually the stay condition. It's just the meaning of ones and zeros on the input to change. So that's a stay, and this one here is a set. Okay, that's a stay. Okay, so we're gonna stay, and this one here is the one that like the one that isolate, and that's the one that is illegal. So we can have it that way. But why do we care about it constructed using NAND gates? As it turns out, the inputs here S and R, like the minute they change, the output will change as well, and I have no control over it. In storage elements, we'd like to have some sort of a control. So what we do is we add some sort of an enable signal, and that enable is actually what we usually connect a clock to. So what you see in here is what we call a gated SR latch. So I added these couple of NAND gates in here to the NAND implementation of a simple SR. So, and let's see what would that do. And again, or just as a reminder, as opposed to NOR gates, NAND gates give 1 all the time, except if the inputs are both 1. So if it sees a 0 at one of its input, it will output a 1 at the output directly, no matter what. Okay, so let's do this here, as opposed to the other case in here, the 1 to 0. Okay, so it's this is 0, this is 1, and I usually write this because it reminds me how the NAND gate works. All right, so let's see that. So according to this characteristic table, if the clock is 0, let's see what the clock 0 means. If this clock is 0, well, I saw a 0, that means this one here is a 1, and this one here is a 1. And according to the set reset, remember, it's like, I mean, the set reset for the NAND gates is a little bit different. The 1, 1 is actually the stay condition, so it actually stay as is. And the way we actually represent it on a characteristic table is by saying QT plus 1 is just equal to the QT. Okay, QT plus 1 is the future value or the next value, and QT is the current value. Okay, so it stays as is. So now if we change the clock from 0 to 1, now the NAND gates doesn't care about that value anymore. It just cares about what S is and what R is. So let's see, what are these values? What would they be? And they would be the following. So if this is a 1 and this is a 0, that output will be 1. So technically, if S is 0, now S is 1. And the same argument can be if this is 1 and this is 1, the output will be 0. So technically what you see at the output of this NAND gate is just S prime or S bar, and this will be R prime or R bar. And now what I have in here in the table is just a normal SR latch. So if you actually have your clock at 1, the rest of it is a normal SR latch, but this is the S and R, and it's in the same meaning of the NOR gate. That's why we did the NAND gate followed by a NAND gate, or what we're doing with the NAND implementation, because I want the S and the R to have the same meaning as the very original one with NOR gates. So now I can easily fill this particular table in here. So if I have a 0, 0, that means that's a QT. Okay, if I have a 0, 1, that means the reset is what I care about, so the output should be 0. And if I have a 1 and 0, that means the output should be 1. And if I have 1, 1, that should be the basically illegal condition, so I'm just going to say illegal, okay, all L. And that's how we construct a gated SR latch. And again, that clock here just tells us or gives us some control over when the S and R actually location or changes. So for example, if we set clock to 0, nothing will change at the output, no matter what I do with the S, no matter what I do with the R. So now this case with the illegal case is kind of annoying me and it's bothering me, and probably bothered a lot of early designers, because I don't want to even give the user the option to use it. So an easy solution was, okay, let's take that gated SR latch, and instead of giving the end user an S input and an R input, let's just give that user just one input, okay, and that input will be D. And what we're doing is we're going to connect this directly, and we're just going to connect that using a NOT gate. So if you put a 1 in here, that will be 1 and that will be 0, and if you put a 0 in here, that will be 0 and that will be 1, and that will be opposite to each other. So I can either give S or 0. So what does the D latch actually do? So let's just explore it. The D latch again is a gated type of latch, so it's depending on the clock. So if clock is 0, I don't care what X is or what D is. So its output value will be the current value itself, which is Q of T. All right, but now what about if the clock is 1, the clock here is 1, that means this is 1, this is 1, this is 1. So in here what I have is the following. I have D prime in here, okay, and I have D in here. Okay, so now let's see what would happen. This is just the normal SR latch in here, okay, and the normal SR latch that is using the NAND gates. And probably actually you don't even have to do this here. What you can do is you can think about it like, okay, let's assume that D is 1, so that will be 1, that will be 0. Well, according to the previous diagram, this is set and this is reset. So I'm just going to write it in here. So this is set, this is reset. Hopefully this is reset in here. Well, yeah, that's the input here. So hopefully you get the idea that this should actually set it to 0. Actually, now that I'm thinking about it, and it's like I paused a little bit and thought about it, it's actually not this way. So let's follow it slowly. So we have a D, and that D is actually here as 0. So let's assume that this is 0. Of course, I'm going to use the clock as 1. So this is 1, this is 1. And if D is 0, that means the output here is actually 1. So let's see. Well, we know that if the input of the NAND gate is 0, it will give me a 1. Okay, so that should be a 1 in here, and that should be a 0 in here. Okay, and again, if the input of the NAND gate is 0, that means the output here is 1, and this is a 1, and this is a 0. And what this told me is the following. If the, let me just write it in here. If D is 0, okay, if D is 0, the output will be 0. And you can follow the same type of argument in here and say, okay, let's assume that D is now, let me just remove these blue ones in here, okay. And let's assume that D is 1, that means this value is 1 in here, and this value here is 0, and this is here is a 1. Okay, so 1 and 1 is 0, 1 and 0 is 1. Okay, and that gives me, this is a 1, and this is a 0, so that will be a 1. So this will tell me the following. If D is 1, the output will also be 1. Okay, and that's why sometimes we call the D latch the invisible latch, because whatever you put in the input will appear in the output as long as the clock is actually enabled. All right, so that's how latches work. So latches are what we call level sensitive devices because they depend, the clock is actually set to the value of 1. As long as clock is 1 and D is changing, the output will change no matter what. Okay, so let's see how that will happen. So in here, it summarizes everything we talked about. This is a graphical symbol. So the graphical symbol tells me that you have a latch. That latch have an output, a Q and a Q bar, and it takes a clock as an input and takes a D as an input. And the characteristic table, exactly as we filled it, it should take like whenever you put a 0 in here and the clock is at 1, the output will be 0. The timing diagram actually shows me that particular functionality. What the timing diagram shows me is the following. As long as clock is at 1, it's basically high. Okay, the input D will be reflected at the output. So let me just highlight these in green so that you can see it. Okay, whenever is the clock as an input is actually 1, the output will be reflected exactly as it is in the output. So in here, so I have a D as 1, this is Q as 1. I have D as 0, that means Q is 0. I have D is actually changing during that clock cycle, and I see the same exact change at the output. It's the same goes in here. It's changing, and it's the same type of change. Now, anywhere else, no matter what, like let's assume in here, okay, anywhere in these particular one in between them, anywhere in between them, you can follow it and you can see that no matter what you do with the D, the Q will not change at all. So that's why we call these type of devices, latches, are level sensitive, because they're sensitive to the level of the clock. So it's expecting like whenever the clock is here is at 1, the output will be reflected. So it is desirable not to change all the time or more than one time within a clock cycle. So we usually use what we call flip-flops. And flip-flops, instead of just being able to change multiple times, kind of like what happened in here and what happened in here, changing multiple times within a clock cycle, going between 1 and 0 or 0 and 1, what flip-flops allows us to do is to change only once. And we can construct the flip-flop using latches. Actually, there are multiple ways to create flip-flops, but the simplest of them is actually to take a couple of latches, and these are actually D latches, okay, connected in a master-slave connection. So we'll see that this particular master in here is connected directly, the output of this is connected to the input of the slave, but the clock is actually connected in an interesting way. So let's see how this actually works. So let's assume that you put 1 in here, and the clock happened to be 1. So what happens is now this particular latch is enabled, and whatever you put on the input will appear on the output, and it will keep changing. 1, like you put a 1, it will be a 1. You put a 0, it will be a 0. Whatever you put on the input will be on the output. However, that in here is not the same because for the slave latch, because the output or the input for the clock here is 0. So this particular one is actually deactivated. So no matter what it's on its input, nothing changes in here. So now let's assume that at some point you have D is 1 and the Q output is 1, and then clock changes from 1 and it becomes 0. So when this becomes a 0, at that particular moment, this becomes a 1 in here. And what happens is whatever is at the input of this particular latch will get sampled and outputted to the output in here. Okay? And that will be 1. And now, no matter what you do at the input of this latch in here, well, the clock is 0, nothing will change in here. So what does this do? Well, it tells me the following, that when I get a negative edge of the clock, when I moved this one here, I just showed you, when I move from 1 to 0, that's what we call from the top to bottom, or the falling edge of a clock, or the negative edge of the clock, I will get an output sample. So let's see the timing diagram for this little guy. So this little guy in here shows me the clock, shows me the D as an input, shows me the QM here for the master, and the QS for the slave, and the Q for the whole flip-flop. But what I really care about is are these in here. The negative edge of the clock, which is right here, and the negative edge of the clock, which is right here, or the falling edge sometimes it's called. We call it negative edge because this is how we describe it in Verilog. Okay, so that tells me that this is when D will be able to change. Other than that, D will never change outside these particular moments. So as you can see, or not Q, sorry, the output in here, you'll see that the output is only changing here, it's only changing here, and it's only changing here. So now I restricted it to change exactly at an edge of a clock, not everywhere. And these are how flip-flops generally work. This isn't the only way we can construct flip-flops. There are other, probably more efficient way and less gates, but this is an easy way to explain it. This particular flip-flop is what we call a negative edge triggered. So latches like this one and this one, they're called level triggered because they'll change no matter what whenever the clock is at 1. But flip-flops are edge triggered because they're triggered by some sort of an edge of a clock, whether it's the negative or the positive. In here, I just showed you a negative edge of the clock. If I wanted a positive edge of the clock, I can easily do it by changing a little bit of this here by saying, okay, I'm going to put the NOT gate in here and I'm not going to put any NOT gate in here, and it will change the positive edge of the clock. At that point, you'll have the changes happening in here at the rising edge of the clock or the positive edge of the clock. All right, so as a summary, what we've seen is we've seen 3 types of devices in here, actually 2. It's a D latch, okay? The SR latch are internal to these D latches, but these are the most basic storage elements. They're called D latches and D flip-flops. So a D latch is actually a level triggered, and that's why we see the clock written this way, as opposed to D flip-flops like this one and this one. So let me just write this here. This is a latch, and this is here is a D flip-flop, and this is here is another D flip-flop, okay? So we know it's a flip-flop because the clock has a little triangle in here. So I know it's actually edge triggered, it's not level triggered. This little circle here tells me it's negative edge triggered or falling edge triggered. It's exactly the same as what we've seen in here without the modification. And this one here tells me it's positive edge triggered.